Good day everyone, my name is Levinas Sumukalangan. We are Group 3 to discuss our final project in Communication 3. I will present my group mates in this project. First, Samantha Danipog, Charmaine Dizon, Iyomi Federico, and lastly, Randolph Dumaano. We will also discuss our title, objectives, intended learning outcomes, discussion, resources, procedure, conclusion, and lastly, our assessment. This project entitled Design of Three-Dimensional Radiation Pattern of Dipole Antenna. Our objectives: this activity aimed to design a program that plots the radiation pattern of dipole antenna in three-dimensional form. 2. To design a program that plots the radiation pattern of dipole antenna in two-dimensional form. Also, our intended learning outcomes: at the end of this activity, the student shall be able to model an antenna structure. 2. To simulate a MATLAB codes or program to implement the calculation dipole radiation expression. 3. To compute the characteristic of radiation function of the antenna. And lastly, number 4, to differentiate the effect of separation distance, number of isotopic antenna, and the phase angle of the dipole radiation pattern.
So for the discussion of the design experiment, radiation is the term used to represent the emission or reception of a wavefront at the antenna, specifying its strength. The energy radiated by an antenna is represented by the radiation pattern of the antenna. Radiation patterns, or diagrammatic representation of the distribution of radiated energy into space as the function of direction. The radiation pattern of any antenna can be plotted. This is plotted into a polar diagram. A polar diagram is a plot that indicates the magnitude of the response in any direction. At the center of the diagram is a point referred to as the origin. This is surrounded by the curve whose radius at any given point is proportional to the magnitude of the property measured in the direction of that point. Polar diagrams are used for plotting the radiation patterns of antenna as well as the other applications like measuring the sensitivity of microphones in different directions, etc. The radiation pattern of a dipole antenna is of particular importance for many reasons. It needs to be oriented so that it picks up the maximum level of signal or radiates a maximum amount of signal in the required direction. So for the additional information regarding radiation antenna, one of the applications for this type of antenna is the ground mapping, wireless body area networks, and it is used in 5th generation network or 5G applications in the University of Arkansas. For the procedure of the design experiment, it is divided into two parts. So part 1 would be designing 3D structure, while part 2 would be designing 2D structure. Step 1, design a 3-dimensional radiation pattern of dipole antenna in MATLAB using the expression of the radiation pattern formula. So this is the formula for radiation pattern, wherein KL stands for the length of the antenna and theta is the angle of elevation or the phase. Step 2 contains all the given values such as degrees from 0 to 2 pi, the interval of 0.12, and the length which is 0.01 meters. So in part 1, the codes are already provided. However, it still needs some modification. So to modify the code, we need to change the data with respect to the given values in step 2. So as we run the program, Step 3 suggests that the scaling of intensity of the initial output is incorrect. So therefore, we expect that in the data and result, the final output should be represent the correct scaling of intensity, where red means high intensity and blue means low intensity. So for the part 2 of the procedure, in step 1, create a program that will design a dipole radiation antenna in 2-dimensional form that contains the number of isotropic antennas, phase angle, separation distance, and the wavelength. So in this part, codes are not provided in the procedure, thus it is evident that we need to provide a program that will ask the value of wavelength, number of elements, value of phase, and the separation distance value that will be used in a certain formula to generate two-dimensional form of a dipole radiation antenna. And for the remaining steps, specifically step 2, 3, and 4, it answers the intended learning outcome number 4. So wherein in order to differentiate the effects of separation distance, number of isotropic antennas, and the phase angle of the dipole radiation pattern, we need to vary the value and set the other specification to be constant. So throughout the last procedure, we all vary the values of the specification except the wavelength. So we set the wavelength to be equal to 1000 kilohertz. So for the simulation, first we need to copy the codes provided in the procedure and paste it to the command window. Since it still needs some modification, we will change the data with respect to the given values. So this presents the initial output. So notice that the color scale is incorrect. Therefore, to change it to correct intensity scaling, in the menu bar, click the figure and click Edit, then Property Inspector will appear. Property Inspector are used to modify generated output. It specifically pertains to the three-dimensional structure. So under Color and Transparency Map, change the color map from Parula to Jet. And now we have the correct color scaling of intensity, where red means high intensity and blue means low intensity. So for the part 2 of the simulation, we have created codes for two-dimensional radiation pattern of a dipole antenna, wherein the program may vary its specification. So lambda, N, alpha, and D are the specifications we want to vary. So basically the program will ask for the user for the value of wavelength, number of elements, value of phase, and its separation distance. So for the formula, we use beta to represent the wave number. So wave number is the quantity 2 pi lambda, which occurs in the mathematical description of wave motion. So if you write a wave function as sine kx minus angular velocity t, the argument of sine function would be in radian. So k multiplied by x must be in radian. So k has a unit of radian per unit distance, which is 2 pi per lambda. Then we also set an interval for theta from pi over by 100 to 2 pi, and pi over 100 is basically near to 0, which is approximately equal to 0.03. So for the simulation, copy the codes and paste it to the command window. Then the value of wavelength is equal to 1000 kilohertz, the number of elements be equal to 2, and the phase be equal to 0 degrees, and the separation distance equal to 250 meters. So separation distance formula is basically wavelength divided by 4. So our wavelength is equal to 1000 kilohertz divided by 4 is 250 meters. So this will be the output. So again, copy the codes. The value of wavelength is equal to 1000 kilohertz. The number of elements is equal to 4. The value of phase is 0. And the separation distance is also 250 meters. So the output will look like this. Then copy the codes. Repeat all the constant and let the number of elements be equal to 8. So the output should be like this. So for the next tabulation, we're going to vary the value of the phase or degree. So with constant wavelength, 1000 kilohertz, number of elements equal to 2, and separation distance equal to lambda over 4, which is 250 meters. So phase is equal to 0 degrees, 45 degrees, and 90 degrees.